โอเคครับ
ครับเป็นลายมือนะครับ
ได้ครับอาจารย์ดีครับ ก็ถึงเวลาพอดีเลยครับอาจารย์เริ่มเลยไหมครับ
ครับได้ครับได้ครับ
Okay, so welcome everyone again to this final session. The speaker is Professor Dr. Jessada Tariboon from King Mongkut's University of Technology, North Bangkok. So our neighbor university. He will give a talk on fractional calculus and differential equations. And thank you very much, Ajahn Jessada, for accepting our invitation to give this talk. You can start when you are ready, and you have around 50 minutes, so you do not need to rush on your talk. Okay, so I'll hand the microphone to you now.
Okay. Thank you very much. Hello, everyone. Today, I would like to talk about fractional calculus and differential equation. My name is Professor Jessada Tariboon from King Mongkut University of Technology in North Bangkok. I will present about the idea of calculus. I would like to go to the past to see the Newton. Newton saw the object in the space, and he saw the object move from one place to another place, and he saw, but he cannot saw the object for every time. He have to eat, he have to sleep, he have to anything to do. He can saw some discrete of the discrete time of the mass. So he defined the velocity to predict. For example, if he saw the star and he go to bed for sleep, and next day he saw the star in another place, so he can calculate in the paper where the star is by use the quality velocity. Go back to Newton and Leibniz. Newton and Leibniz introduced calculus but use different notation. Newton used dot, but Leibniz used d by dt. This is the first derivative. For the second, Newton used double dot, and Leibniz used d square x by dt square. He put the number 2 here. But in the Newton work, he studied about velocity, about the first derivative and the acceleration, the second derivative. But if the higher order, the third derivative, triple dot, and the third derivative by Leibniz, the fourth, is difficult to use the Newton symbol because there are many dots. But in Leibniz notation, change only the number. And for n derivative, Newton notation used n dot is difficult to use, but Leibniz used this notation and write this n. Then after that, Leibniz, no, not Leibniz, L'Hopital. I think Lobitan live in German. Lobitan saw the Linus notation and asked the Linus if n is equal to 1/2. This. And know that anyone in England asked Newton what happened for this notation? X half dot. So the fractional appear in German, not in England, because the notation of Linus. And in year 1819, Lacroix introduced observed the derivative and derivative of polynomial. If x equal to t 5 and the first derivative is equal to this, the second derivative equal to this, and the third derivative equal to this, then he get the idea to use the notation of factorial. 5 multiply 4 multiply 3 equal to 5 factorial over 2 factorial. Yes. And he get the formula for any n derivative. N is the odd integer. N is the integer. In that time, the world not have the grammar function. When the time passed, the grammar function was born. The grammar function connect between discrete value factorial. For example, 0 is 1 factorial. 1 is 1, and this 2 factorial, 3 factorial, and the gamma function can connect between all points. You see this. Then from this formula, the mathematician replaced this formula, this term by gamma function. By gamma function, because the gamma function can connect between all points. This D, C, B, and A here. The gamma function is defined by this. This is the relation of the gamma function and the factorial function. And this is a formula of gamma function in the form of improper integral. Then the formula of n-time derivative can be replaced by the gamma function. And the mathematician can replace the integer order here by arbitrary order. Alpha is the arbitrary, greater than or equal to 0. For example, the half derivative of t by use this formula. Replace alpha by 1/2 and beta by 1 and get this formula. So if we see the alpha order derivative is like a mapping from the function ft. For example, if f is t squared and alpha equal to 1, the mapping maps t squared is a part of parabola to be the line, the straight line here. We can see the arbitrary order. This alpha equal to 0. This the parabola. And when alpha equal to 1, it is a straight line. And when alpha is 0.1, 0.2, 0.3, 0.4, 0.5, yeah, we have many graphs. Then the fractional derivative operator is mapping from this function to the function between here and between here. You see, it's up to the order, fractional order. Okay. Next, we will see the application. Why we study differential equation, why we construct the differential operator, why. I would like to give some application to talk about the story of Marie Curie. Marie Curie is a woman. She get 2 Nobel Prize. She was born in Poland, and she went to France to study mathematics and physics. She found the radium, the radiation of radium. She got the Nobel Prize in physics in this year and Nobel Prize in chemistry in this year. She discovered the radiation of radium. The radiation means if we have the object or matter, if the time pass, the matter is reduce the weight, like half-life. When some scientific calculate the the half-life of material. If 2 students ask Curie, if one student have the radium, 1 kilogram of radium, and how about the weight of radium in the next 500 years? The radium have to reduce the mass. And how many the mass in 500,000 years? So she start to give the answer for 2 students. She put the radium 1 kilogram and measure the weight of radium. And 1 year passed, she calculate and measure the radium. And 2 years passed, she measured the radium again. But she cannot measure the radium for 500,000 because she dead. She dead because human life not long. Human life not long. So how Cooley give the answer for two students? She used differential equations. She measured at this year and measure the weight this year and minus this year, and she create the model by use the chemical process. And next, she measure this year and minus this year to this. And next, and after that, she transformed all detail, all information to be differential equation. And she solved. Yeah, not for 500 years, 500,000 years next to know about the weight of the radium, but she put T by 500,000 and she can give the answer. This is a very important thing to study differential equation. That is scientific measure some value of phenomena and want to know all the value all the time and can predict all the time. And this is the importance of the differential operator because we don't know this is a good or the best differential equation because now it's not equal to 500,000 years. Maybe if she put this by fractional, maybe give more, give the best solution. Next, I have to present about how to formulate the formula of fractional integrals. We start by to see the double integral by changing variable. This integral is this direction. This integral for this direction and this integral for this direction. From change variable, we can the double integral can be right in this term, and this term can be formulated by this term. After that, observe the triple integral. By use the above method again and can get this formula. This for triple and fourth integral can be right here. Then for n time integral, it is a factorial function again, and if we want to construct the formula of fractional integral, then we change from factorial function to be grammar function. This is the symbol of n time integral, n time integration, and used to be grammar function. If we saw this by we have the above, we have this formula, then we can use the above formula by by use the beta function. Beta function defined by this. This is a special function, and the beta function can be write in terms of grammar function by this. So if we want to formulate the n time integration of t power m, we put t power m here and use the above formula. From here, we set another variable, set u equal to s over t. Then we have ds equal to t du. And we replace this to the above formula. We get this. See, u now ds and this du, this s equal to 0, s equal to 0, and u equal to 0. If s equal to t, s equal to t, s equal to t, t over t, u equal to 1 here. Okay, then du integration from 0 to 1. By changing variable. After that, this is the formula of beta function. Then we can replace this term by the beta function and convert the beta function to be the grammar function again, and this grammar function can be deleted by this. Then we have the formula like this. This formula seems like the formula of fractional derivative. If we replace n by minus n, if we replace n by minus n, this minus n, this minus n, then we have the formula of fractional derivative. I'll show that. This is the formula of integration. Integration is positive. But if the formula for derivative, this minus. After that, from this formula, the Riemann will replace n by alpha. They replace n by alpha. Alpha is arbitrary order. Alpha here and alpha here. Okay. Then they define the Riemann-Liouville fractional integral. And in addition, they define the fractional derivative, namely Riemann-Liouville fractional derivative. Let alpha between n minus 1 and n. Then the Riemann derivative can be right here. Observe that the Riemann, the integer order is left of I. The integer order the derivative of integer order is the left of I here. Can be separated in two cases. Alpha between minus n minus 1 and n, and alpha equal to n. But the Riemann-Liouville derivative of constant not equal to 0 is it not meaning in mathematics, but in physics, okay, for the formula of Riemann-Liouville is okay, and many physicians like the formula of Riemann-Liouville fractional derivative. But in mathematics, many problems not like, because the derivative of constant is not equal to 0. Then they define the capital fractional derivative. The capital is different from the Riemann. The Riemann have the integer left, but the capital, the integer order light. This is the difference of two definitions of Riemann-Liouville and capital fractional derivative. The formula of the capital fractional derivative is here. Observe that if f is constant, you see, if this is constant, so the derivative, because this is the integer derivative of constant is 0, then the fractional derivative of constant is 0. But both derivatives not equal. The difference can be right here. Okay, this is a initial value. Next, I would like to present another definition of derivative, namely delta derivative. Delta derivative right here, t d by dt. Delta derivative is different derivative from the usual derivative. If the n order derivative right here, but the delta is delta derivative of log t equal to 1, derivative of log t square equal to 2 log t. Derivative log t third equal to 3 log t square. It seems like derivative of power function. Seems like derivative of power function. And delta derivative, the second derivative of log t third equal to 3 times 2 log t square. And then the derivative of order alpha log t beta equal to this, because it seems factorial function in the same way to derive for this formula. And how the importance of delta derivative in application in the book of Kivas theory and applications of fractional differential equation, write about this delta derivative. The importance in the special function, namely Bessel function. Delta n of this function equal to this. This is significant to study the delta derivative. Next, delta integral. It's not a well-known notation. I use this notation only in this presentation. Delta minus 1 of f equal to integration from 1 to t f s ds over s. Integration 1 equal to log t. The double integral of 1 equal to t square over 2. We observe this significance of this. And we have the n time integration of delta integration is this formula. And you see, this is factorial function. Mathematician, namely Hadamard, replace this factorial by grammar function and define the Hadamard fractional integral like this. You see, replace this by this. And the kernel is log t over s or log t minus log s. I compare between the Riemann-Liouville fractional integral and Hadamard fractional integral. This is the formula of the Riemann-Liouville fractional integral. It's the same, the grammar function. And the kernel t log t s log s. And he is Hadamard. Hadamard is a famous mathematician. He studied many inequalities. The famous inequality is Hermite-Hadamard inequality, and used in applied in statistics. For the Hadamard fractional derivative, defined like this. Hadamard fractional derivative defined like this, and Hadamard fractional derivative in the sense of Caputo, because this derivative, this formula, this derivative of constant not equal to 0 again. This derivative of constant is not equal to 0 again. So mathematician define Hadamard in the sense of Caputo by remove the delta derivative here to inside. You see, this is the delta derivative. Move the delta derivative to inside of integration. We can compare between this Hadamard and this Riemann-Liouville. This is the usual derivative, and this is the delta derivative. The gamma function, and this is the kernel t log t minus s log s. Okay, and for the Caputo fractional derivative, this is the same, the gamma function and the derivative inside the integration. So the Riemann-Liouville fractional derivative just like this, the usual derivative d by dt, but the Hadamard fractional derivative just like t d by dt is different. Okay. About 3 years ago, I thought about some new definition, but not new. But in that time, I think new. This derivative e power minus t d by dt, because I observed that the delta e equal to 1. Delta e square equal to 2 et. Delta e 3 times t equal to 3 e 2t, and like this. And I define the integration like this because I observed that delta integration 1 equal to e. The double integration of 1 equal to this, and the triple integral of 1 equal to this. So that time I define this formula, and I have 2 papers about this formula. Also that this is the definition compare between fractional integral this and the Riemann-Liouville this. It's the same gamma function integration and the kernel t e t s e power s alpha minus 1 is the same, and like this. And the sense of Riemann-Liouville, the derivative outside, the integer derivative outside, and this is the same, the gamma function and integration and the kernel, and the fractional integral in the sense of Caputo, the integer derivative, the derivative of integer order inside. and this is the third line of this derivative. But in that time, I don't know until my friend told me, Jessada, see the book of Keybass again. The book in the chapter 2, in the section 2.5. This is very general. Fractional integrals and fractional derivatives of a function with respect to another function. Yes. Defined by this. D with respect to g. G is a function. The function is the increasing function, g prime greater than 0. Wow. Define this. If gt equal to t, if gt equal to t, this is the usual derivative of Newton. And if gt equal to log t, this is the delta derivative. Delta derivative like this. And if gt equal to e power t, this the derivative of y was introduced previously. So this formula is very general. And observe that dg of g equal to 1, dg square equal to 2g, dg 3/3. Third derivative equal to this. Oh. And the integration defined by this. If g0 equal to 0, we get integration 1 equal to gt. The double integration of 1 equal to 1 over 2 g square. And the third integration g of 1 equal to this. So in the book of Keybass give the definition of fractional integral with respect to function g by this. We can compare with the Riemann-Liouville gt equal to t, gt equal to t, this t, gs equal to s, this s, and gt equal to t, then g prime equal to 1. Okay. If next we compare with Hadamard fractional integral. Okay, this gamma function, and if gt equal to log t, gs equal to log s, and g prime derivative of log is 1 over s. Oh, it can be reduced to this, the Hadamard formula. And next we see the definition of Riemann-Liouville fractional derivative with respect to function g by this. Observe that the integer derivative is in the left side and the integer derivative is inside the integration. I think it's finished. Oh, I have another part. Proportional fractional calculus was born in a few years. It is another sense of fractional calculus. They define. I would like to delete some graph. If you have two graphs, one graph is t square and another graph is 2t. The proportional derivative defined by this. D low f equal to 1 minus f 1 minus low ft plus this. Low between 0 and 1. If low equal to 1 over 2, this point, yes, 1 over 2. So for example, this A, this is GA, this is FA. And low is 1 over 2, then between the middle between 2 points. And this again between 2 points here and here. This again between 2 points. Between 2 points. Then we can draw the graph. This graph is the 1 over 2 what function f. And mathematician delight G by replaced by F palm. This is the graph between F and F palm. This F and this F palm. The derivative of F. So the name is proportional. They delight and get this formula. So they define the proportional integral by this. And they formulate the n time integration and get this formula. So for arbitrary order, they get this formula and they define the derivative and the n time derivative, and they get this formula. And this is some properties. I got this paper from one student of Poom. This published in 2018 by this mathematician. Okay, I'm finished to present about fractional calculus. Thank you very much.
Okay,
Hello.
thank you very much, Ajahn Jessada, for your nice talk and a lot of illustrations which explains the concept very well. So I'd like to ask the audience if they have any questions. I think many people in the lab is working on the topic. Okay, it is. Please.
Thank you, Professor, for the nice talk. I want to ask about this generalized fractional derivative generated by proportional. Yes, I and Professor Jared tried to define a capital in the capital sense, that is the generalized proportional derivative generated by in forms of capital with respect to another function. But
yes,
but actually I'm facing a problem, especially when apply the Riemann logically to the operator, the semi-group property.
Oh.
But I don't know if you can, maybe since you read the paper, you understand the setting.
Yeah, you the semi-group property, right?
Yeah, the first paper we defined the Hilfer operator in this setting. The Hilfer in the sense of yeah. But when we try to define a fractional derivative with respect to another function in the sense of Hilfer setting, we could not get the semi-group property.
Yeah, maybe you come to see me and discuss about some computation if you have problem.
Okay, no problem. Thank you.
Okay.
Okay, so are there any further questions?
Yes. I have
okay.
One question.
Yes, Paula, please.
Thank you, Professor, for the nice talk. I want to know that on slide 27, you mentioned that you thought about the new derivative in terms of exponential.
Yeah.
And later you find out that they have presented a generalized such kind of generalized derivative.
Yeah.
So I want to know that the derivative you proposed is, I mean, I want to know about the physics behind that derivative, that how it is different than the usual derivative in terms of physics.
In terms of
In terms of physics.
physics, no, that derivative not me. Oh, this not meaning in physics because I only observe the property of, for example, because I know uh, the usual derivative, I know the delta derivative, so I want to construct another derivative, and I observe that, hey, if I define by this and I take this is equal to 1, it take this derivative equal to this is close to the usual formula. And in that time, I don't know the formula of the generalized formula. I observe only this, and I construct this, but it is a special case. It is special case of fractional calculus with respect to another function in the QBAS book. This is special case. So I study about only 2 papers and I finish because it's special case.
Okay, okay.
Okay.
Okay, so any more questions?
No, I don't want to leave. No. I want to stay here, but I don't want to listen anymore.
Okay, I'd like to know, you have so many concepts of fractional derivative, and you also showed the graph when you when you change the parameter alpha from 0 to 1.
Yeah.
And you also have the property that when you take the fractional derivative of a constant function, it's not 0, right?
Mm-hmm.
In that case, I'd like to know what kind of behavior when you change alpha from 0 to 1, because when alpha is equals to 1, the derivative is 0, right?
Yeah.
Yeah, and when, for example, if we define a function fx equals to 0, so a constant function, and you take the fractional derivative with alpha in between 0 and 1, what happens in that case? How it will look like?
Oh. For example, the Riemann this is the formula of fractional derivative of constant equal to this. So
Okay.
the graph is singular.
Okay.
Okay.
Oh,
This
very
is a
strange.
amazing formula from appeared from the Riemann-Liouville fractional derivative.
Okay, and it only defined for t positive. At t equals to 0, you don't have the derivative, right?
T. Yes. You're right.
Okay. One more question out of my curiosity. Normally, when we take the derivative of the exponential e to the power of x, it is e to the power of x itself. How about the fractional derivative of that exponential function? Is it always the same?
By use computer only, because it not have a explicit formula.
But it's not e to the power of x, right? It's not identity, right?
Yeah.
Okay. Very strange.
It's difficult. We change the function.
And does it has any property related to the power series expansion of a function? Because when I see also from the morning, and also in your presentation when you present the difference between two fractional concepts, it looks something like the power series expansion.
It's only initial condition.
The non-local one, or
you mean
when you when the difference, for example, in the second line, you have the Riemann fractional of f equals to the capital fractional of f plus this series, finite series.
Yes.
Does this related to some kind of power series expansion of a function? Just wonder.